than the span. So the span of S is actually the smallest vector subspace of V which contains S. Okay? Obviously we observed that as we make our subsets bigger, the spans also get bigger. The span of the empty set is the zero, the smallest subspace. The span of a set is equal to it if and only if S itself is a subspace
is the case. It's full. Okay.
And the span of, so this one says, the last one therefore says, so these were the main results that we did last time. Okay? Now, as I was saying, this and what we do today is actually the backbone of this course. Okay? So this is the most fundamental notion in this course is about this span and what we are going to do today. Now, so we start today. So we looked into these, which are, so we will say members of span of S as, this is how we will speak of it. We will say, call the members of S as finite linear combinations. Of members or elements or vectors obviously the empty linear combination when n is 0 gives us x equals 0. So that's how we'll understand it. Empty linear combination is 0. Okay? So these are all finite linear combinations. And well, I believe the name itself is quite suggestive. This is linear combination, this fact. Okay, so it's quite suggestive. So now, so we will go on calling such things as linear combinations and so on. So now my question is this representation? So what we are doing, so span of S is precisely the collection of all those vectors which can be represented as a finite linear combination of members of S. Now is this representation unique? So what do I mean by this? Suppose I have a vector X which is a linear combination of, which is a finite linear combination of some vectors S1, S2, Sn. By asking whether it is unique, I'm asking this question, what happens if it is not? I think this is someone, please can you put off your microphone?
So you know how to use it. Whenever you want to talk to them, you press.
Alright.
So this is for your aircon.
Alright.
So you can control the.
Can you please switch off the mic?
It's up to you because you're the one who's attending the number 13. Yeah, so then tell her, oh, yeah, you must feel this.
So this means if I take things to one side,
Yeah.
For engineering students
For PhD.
in,
Mathematics. Excuse me, sir. Yeah.
you want to be a mathematician.
Yeah. Excuse me, sir.
can people on the other side
It's
close their
Middlesex. Can they switch off their
microphones,
mic?
please? So if I have x represented in two ways, it is actually telling me that I'll have such an equation. Okay? I'll have some such thing like this. So the demand of uniqueness is equivalent to saying so given some such thing like star, alpha 1 minus beta 1 must all be 0, which is the same thing as saying that alpha 1 is equal to beta 1 okay? So this is where we come to hit a very, very important notion. We will say that, well, we don't say in terms of sets, no, because there is something to do with this S1, S2, this order also. We will see how it is very important. So we will actually say, so this is our definition. So, if let's say, let's give this a name, say this, okay. n tuple of vectors from V is said to be linearly independent if this implies that means zero can, so a list of or an n tuple of vectors, n tuple is also another name is list. In a listing you always have an order. The first one in the list, the second one in the list, and so on, right? So I'll also use the word list. So a list of vectors is linearly independent if whenever you have zero represented as a linear combination of the vectors in that list, then it is the trivial one.
It is was already Shijat.
Okay? It is the trivial representation. So you don't have any non-trivial representation of Z. Okay? So for instance, observe. So observe. The singleton, this one, is linearly independent if and only if yeah? So, if you have a bigger list, if a list be linearly independent, then any smaller list, or let me use the word sublist, although I have not completely told you what is it, but it is quite understandable. Say, okay, where if you take anything, any one of them in between, okay, is also linearly independent. Okay? And we don't say a list is not linearly independent, we say it's linearly dependent. The list which means, therefore, that this statement is false. That which means that there will therefore exist. So it means that there exist not all zero, such that, sorry, that means you can write zero non-trivial. Alright? That is the whole idea of saying that the list is linearly dependent. Okay? Now,
Excuse me, sir.
the next, yes.
Just please, by the way, when you use the different colors, what do they mean? What does blue mean?
Okay, let us make this convention that usually I will be writing in black. Blue means I'm defining some notion.
Okay.
Red shall always be the statement of a theorem or a result. And green shall be the proof of the result. Okay?
Okay.
So, instead of falling back again and again and again on this definition, here is a nice way to show that a list of vectors is linearly dependent. So this is quite helpful. So let's record it. A list understand this. So given 20 vectors, this immediately says, if you have 0 in that list, so given a list of 20 vectors, an upshot of this is, if 0 is there in the list, it is linearly dependent. If not, try and see if V2 is a multiple of V1. No. If V3 is a linear combination of V1 and V2. No. And so on. Okay? So you see, it is an algorithm, right? This statement itself is an algorithm. Suggests a way to see whether it is dependent or not. Okay? So before coming to the proof, let's look into the algorithm. So what does it, so given this list, let's have another color for this. So we are given this list. So you start off with k equals 1, and then you ask the question, if Vk is 0, if it is, your answer is linearly dependent. Okay? If not, then you ask the second question. And what is that? Little bit. You start from k equals, I'm sorry, k equals 1 doesn't have this. You started with k equals 1, and you increase it to one more. Okay? And then you ask the question, okay? If the answer is yes, you're back here. If the answer is no, you go back here. If the answer is no, you go back here and you continue until you reach the end. And no, in fact, you go back again to the same place. Okay? So, that's the whole idea. You see whether V1 is 0? No. Whether V2 is a multiple of V1? No. So whether V2 is 0? No. V2 is a multiple of V1? Still a no. Next step. V3, whether it is 0? No. Is a multiple of, it's a linear combination of V1 and V2? No. Next step. So you go on until you have an answer yes. The moment you have an answer yes, you decide. So you see, it's a shortcut way, it's a definitive algorithm to test whether a list is linearly dependent or not dependent. Okay? Good. So now so having understood this, let's see how do we prove this. Well, the proof the if part that is trivial. Because what does if part say? If part says that either for some k between 1 and n, Vk is 0 or Vk is a linear combination of the ones before. Right? So then you know already that you put if that k, say n is 20, and you tell me that for k equal to 9, V9 is 0. Means automatically it's linearly dependent, right? Or you tell me that V9 is a linear combination of V1 up to V8. Okay? Then you take that linear combination and for the rest up to 20 you put the scalar 0. Your answer is still a non-trivial expression, representation of 0, right? So it's linearly dependent. Okay? So the if part is trivial. So we only need to prove the only if part. So what is given? Okay, so then there are scalars. Not all 0, such that now, not all 0. Well, there's a problem over here. I don't know which ones are 0. You have just given me scalars. So, depending on specific instances, some will be zeros, neither could be 0. There are several possibilities. But we'll have to find out a way to give a proof for all of them. Okay? So what do I do? So I take to this trick, let P be the set of all natural numbers such that P is greater than or equal to 1 and there are scalars such that Okay? I collect all those natural numbers. You will see why I did this. Obviously, T is non-empty. Because N itself is in T. Okay? Alright? Now my next question. What do I do? Now, every non-empty set of natural numbers has a smallest element. Right? So this is the crucial fact that I am using. So every non-empty set of natural numbers, let me see if I can introduce a page. No. So I'll have to go to the next page, but I cannot introduce a page. That's quite strange. Okay. So here is a fact which I need for natural numbers. So are necessary. And you must have seen this in your previous course. Every non-empty subset has the smallest element. So this is an important fact of natural numbers. So now, coming back to our T. So T, remember T is the set of all P in such that P is greater than or equal to 1 and beta 1 B1 for some scalars. Okay? And we have seen that this is non-empty. And, okay. So, T is non-empty. And hence, has a smallest element. Hence, there are scalars such that what can you say? Further, you can say something more. What can you say? You can say beta k is definitely non-zero. Why? Suppose if beta k is non-zero, is zero, then this actually gives you a natural number in T which is smaller than K, which is not possible. Right? Okay? So, and hence, that is what I was requiring. Why did I say all of that? That the moment you said that A1, A2, AN is not all zero, why did I take this route is because I didn't know whether AN is zero or not. Okay? Initially. But now I have a way to ensure that beta k is non-zero. And hence, I can write beta k as which implies now you say, what about the other one? Yes. I was just waiting for you. Now, let me repeat this. If beta k is non-zero, it's just not only this. There's also another possibility. And that is, Vk can be zero. Okay? So, either if Vk is zero, then you already have zero is a linear combination, is a non-trivial linear combination of the previous ones also. Okay? So, and thus, this or Vk is zero. So, from this step, I conclude that either Vk is zero or beta k is non-zero. And then, if Vk is zero, I'm done. And if Vk is non-zero, then I can write Vk as a linear combination of the previous ones. Okay? So that shows, that completes the proof. Okay? So you have the proof of that algorithm which we outlined here. Okay? So this is the algorithm for testing linear independence or dependence of a list. Okay? Alright. So this is a nice little technique. Now, so is this clear now? How do you test? What happened? Which one? How do we test the linear dependence or independence? Okay. So now, let's move forward. Now suppose you tell me the following, that you give me a vector space and then you tell me that there is a list of size n, okay, which is linearly independent and spans that vector space. Okay? I will show now that if this is the case, then every list which is spanning, every linearly independent list which spans that vector space must have the size n. Okay? So, that's my theorem. So given a vector space V and a list which is linearly independent and then every list let me write it, every linearly independent list spanning V has exactly n vectors. So what's the upshot of this? The upshot of this is that if you tell me that a vector space somehow gets spanned by 20 vectors in a linearly independent fashion, then any set of linearly independent vectors which span it will have 20 vectors. So that number 20, or this number, okay, is something very, very special about that particular vector space. Okay? It is independent of the choice of this linearly independent subset spanning it. It also says, oops, now what happened? It also says, therefore, that it is the largest linearly independent, is the largest size of a linearly independent list which can span V. Okay? So, if you have any set of n plus 1 or more vectors, or n, it must be linearly independent. Okay? So that number n is characteristic in some sense of that vector space. Yeah? So that's why, so let's first prove this. The proof is very, very simple. Let independent list and spanning V. What do I do? So in particular, all of these vectors V1, V2, Vn is a linear, since is a linear combination of these primes and the reverse. So by T1, this list introduced one element. Okay? So it's a linearly dependent list, and
sorry, sir.
So what do I do now?
Excuse me, sir.
Yes?
On the proof, when you say let that vector space, the V1 with a dash on top, though, that subscript, V1, V2, Vn, be another linear independent list. And then you say, in other words, V spans then that vector space. When you say so by T1, are you concluding from that list on top now?
Yes. The first C, V1, V2, Vn, it is the initial list that has been given to us.
Yes.
Which spans the vector space V.
Yeah.
So V1 prime, since you have told me that V1 prime, V2 prime up to Vn prime is a linearly independent list,
yeah.
None of them is zero. None of them can be zero vector, right?
Okay.
Now, since V1, V2, Vn, they span V, V1 prime is a linear combination of V1, V2, Vn.
Oh, okay.
So therefore, using T1, this new list that I have taken, which is V1, V2, Vn with V1 prime added at the end, that is a linear dependent list, right?
Okay.
Because remember what was the argument? There exists a K such that so that the vector is zero, or it is a linear combinations of one before.
Okay.
Yeah? So that's
Okay.
why I'm saying. So this is by T1, it is linearly dependent, and I have V1 prime to be this, and you have told me that of these scalars, alpha 1, alpha 2, alpha n, not all are zero. So if yes?
Yeah, so when you say so by T1, do you have V1, V2 up until Vn, then you have V1 prime. Are you saying?
Yes.
But you've already told us that V1 prime is linearly dependent. So I don't know why you're saying so by T1. You're also including V1 prime there.
Well, I'm just making a use of T1 to say that this list
Yes.
is a linearly dependent list.
Okay.
That's what I'm saying.
I see, but you have V1 prime there,
Okay, if you take that, yes, if you take that, that's also an answer, yes. Yes, that's also an answer. Now what happened? Oops. So what happened, I don't really know. Just a moment.
Ya sibayasizwa ke manje. Bheka le yenza.
Oops.
Lecture we don't understand.
No. Yeah, something has happened. I have to. Hello? Hello, Thabo? Something has happened. It has, the board, the lecture has vanished. Okay. Nothing. The mouse is moved. I don't see the mouse even. Okay. Okay. So coming back to that issue, which someone was asking. So you have given me the list V1, V2, Vn. You have told me that list is linearly independent and it spans the whole of V. Okay? Now suppose I start off with another list, V1 prime, V2 prime, say Vm prime.
Okay.
And I also assume that this new list is a linearly independent list and spans V. Okay? Now let me look into that vector V1 prime. V1 prime is already a linear combination of V1, V2, Vn.
Okay.
Because, so, if I make this third list now, which is V1, V2, Vn, and then V1 prime added at the end. Okay, so it's a list of size n plus 1. Okay? This new list is automatically, therefore, a linearly dependent list.
Okay.
Since this is a linearly dependent list, so, and from the fact that V1 prime is already a linear combination of V1, V2, Vn, I have those scalars alpha 1, alpha 2, alpha n, such that V1 prime is alpha 1, V1 plus alpha 2, V2 and so on, right? Now, since V1 prime is non-zero, not all of alpha 1, alpha 2, alpha n can be 0. Okay? At least one of them is non-zero. That's where I got stuck, right? So, V1 prime is equal to alpha 1, V1 plus alpha 2, V2 plus up to say alpha n, Vn. Okay? And of these numbers, alpha 1, alpha 2, alpha n, some one of them is non-zero. I don't know which one. Okay? But some one of them is non-zero. Okay? Thanks. All right. So this is where I am now. So, since one of them is non-zero, so let's say alpha I is non-zero. Then I can rewrite, right? So then I can write, so let me do it. Alpha I, so it's Vi I need a bigger space, so let me do it. So then I can write Vi as.
Can you please go back to the previous screen?
Yeah?
Do you mind? Can you thank you.
Yeah? So if let alpha I prime be not equal to 0, so then I can write this as, let me have,
So just say alpha I prime or alpha I.
alpha I. Alpha I is a scalar which is non-zero. Okay, and so I'm rewriting this in terms of, I'm expressing Vi in terms of the others. That's all that I'm doing. So I can write Vi as so that's why you see I don't have alpha I on the right hand side. So which is okay? And hence, this span, yes? 1 minute, I'll come back, 1 minute. 1 minute. Or let me write. Today this is misbehaving like anything. And this span is nothing else but V. Okay? Further, is a linearly independent span, sorry, in a linearly independent list such that okay? Why is it linearly independent? Let's suppose not. Let's take an expression of 0. Again in V1 prime, I will replace it by the expansion of V1 prime in terms of V1, V2, Vn. And then I'll get an expression of 0 in terms of V1, V2, Vn. Each one of the coefficients must be 0, and from there we will see that it is the linear independence will follow. Okay? So this turns out to be a linearly independent list which spans V. Now, what is the end shot of this? I started off with this. I started off with this one in the proof. I was given this one.
Excuse me, sir.
Okay?
Sorry, excuse
Yes.
me, sir. Look, so on your logic here, you say, just starting off, you say, so by T1, that list is a linearly independent list. Then you say, the list, they are scalars, alpha 1, partial alpha 1 elements of real numbers. Then you say, not all are zeros. Just want to check something. That statement, not all are zeros. What's the logical step that you took for that statement?
Well, suppose if all were zeros, then V1 prime would be 0.
Let's suppose all the scalars are not.
So if all the scalars, alpha 1, alpha 2, alpha n are zeros, then V1 prime becomes 0, which is not possible. Because you have told me that V1 prime comes from a list which is linearly independent. So none of those V1 prime, V2 prime, Vm prime can be 0.
Okay, I get you.
Clear?
But you had said you said V1 prime is a linear combination of V2 prime and
I didn't say V1 prime is a linear combination of V2 prime, because V1 prime and V2 prime are linearly independent.
Okay.
V1 prime is a linear combination of V1, V2, Vn of this initial list that I started off with.
Okay.
Yeah? Okay.
I see.
So now that's what I'm saying. I was given this initial list, as I say, with double tick. Okay? Then I said that let this one be also another linearly independent list which spans it. With this assumption, I have produced a third list, which is this, which has n-1 vectors from the original list Vi's, and exactly one, the first one, V1 prime, from the new list that I started off with. Okay? So see, what did I do? I have just replaced one of the vectors from the original list by V1 prime. Okay? But then, this is also another linearly independent list which spans V. So I can replace some one of them by V2 prime, but that someone cannot be V1 prime because V1 prime and V2 prime are linearly independent. Right? So in the next step, I will produce, by the same argument, I will produce a list like this. Right, which is linearly independent and would span V. And if I go on and on in this way, in n steps, all the vectors would be in a list of
Sir.
1 minute. Right? 1 minute, I'll come back. Yeah? So in n steps, I'll introduce all the vectors V1 prime, V2 prime, up to Vm prime, and get hold of a linearly independent list of length n, which spans V. Right? So, m must be less than or equal to n. Okay? Now, if you reverse the roles of V1, V2, Vn and V1 prime, V2 prime, Vn prime, you would get n is less than or equal to n. Okay? N less than. And therefore n is equal to n. Okay? So you see, the whole idea is replacing one by one. Okay? And that's the whole idea. Yes, now coming back to your question. Someone was trying to ask a question.
Sir, I was
Yes?
struggling with the definition for span. I'm unsure what span means.
So you were not there in the last class and in the beginning of today's class. So here is it. Span of S is the set of all finite linear combinations of S. So either x is 0 or there exists a natural number n and n many vectors from S and n many scalars such that x is a linear combination of those vectors and scalars. Right? And this shows, therefore, we did it in the last lecture, that span of S is the smallest vector subspace of V which contains S. Okay? And that is what we are using today. Alright? Any further? Any more? Where are you? Yes. Next.
Yes, I was looking at the way you wrote these vectors in B1 and B2. Actually from VI, where you say that VI is the element of the span, V1, V2, VI minus 1. But there is that, I don't know, what is the emphasis of that, the change of I to J? From I plus 1.
Okay, one minute. Firstly, so you get that here, what I'm trying to say in this part, what I'm trying to say is I have put VI as a span of vectors, V1, V2 and so on, which are linearly independent, and it doesn't contain that VI. That's why I wrote all that much. Okay, just to show that this ith member, the ith member from the initial list is just missing, and that has come in the span. Okay?
Yes.
Remember, if you don't put in this V1 prime, you cannot write this, because V1, V2, Vn, that's a linearly independent list. So none of them can be written in terms of the others.
All right.
Okay?
Yes.
Okay. So, starting off with V1, V2, Vn, I have come up with a linearly independent list of the same size, but removing one of the vectors from V1, V2, Vn and introducing another one vector V1 prime from the new span new list that I took. V1 prime, V2 prime, Vn prime, right? So that's what I'm doing. But this is again another such list and so on, and I do the same thing in n steps. All the vectors V1 prime, V2 prime up to Vn prime will get replaced. So in n steps I'll be able to create a list of size n, which is linearly independent list and which spans V. So n vectors get inside a list of size n. Therefore m must be less than or equal to n. That's what I'm saying. Okay? So now observe. This was what you are doing with. So you now just reverse the roles of this and this. Okay? So if you reverse the roles, you'll get double inequality. And hence, n must be equal to m. Okay? So that tells me that completes this proof. So that tells exactly what I wanted to show, that any linearly independent list which spans this has the same number of elements. Okay? So that's where I come now. If V be a vector space, such that there exists n exists a natural number n and a list, let me say a linearly independent list, spanning V. Then many things follow. The V is said to be finite dimensional. The unique number so this uniqueness comes from T2, right? Is said to be the dimension. And we write and number 3 that is said to be a basis. Okay? So there are 3 things that immediately come up as an upshot of this. That if you tell me that there is a natural number n and a list, and a linearly independent list of that size, which spans V, then V is finite dimensional. So finite dimensional spaces are precisely those spaces which can be spanned by a linearly independent list of a finite size. Okay? And that finite size is unique for that V, and that is called its dimension, and that independent list of that size is said to be a basis. Okay? Clear? Alright. Now, this therefore, what we have done therefore tells us that the basis is the largest possible, the dimension in fact, is the largest, before I go ahead, vector space which is not finite dimensional so here we defined 3 things. 1, 2, the symbol, and basis. Not finite dimensional is said to be finite dimensional. Okay? Yeah. So so the dimension of a finite dimensional space is the largest size of a linearly independent set. Okay? So any collection of vectors more than the dimension is linearly dependent. Right? Any list of size more than the dimension is linearly dependent. So this is a very, very nice technique to ascertain, but there can exist. So for instance, R1 is generated by any non-zero number, any non-zero element, so dimension of R1 is 1. Okay? 0, 1 and 1, 0, these pairs, generate R2. So the dimension of R2 is 2. Similarly, the dimension of R3 is 3. Okay? Dimension of Rn is n. The polynomials, as I showed yesterday, they are all possible polynomials. If you take, it's an infinite dimensional space. Okay? So, however, in R3, you can have a set of two vectors which is linearly dependent, obviously, right? So, but if you have four vectors in R3, then you know it's obviously linearly dependent. Okay? You don't need to do any calculation at all. Okay. There's one more upshot of this notion of dimension. And what is it? So, suppose I start, so let V be finite dimensional, dimension of V be n, and let's take B be a basis. So for any x that exists, that's where we started off with, right? Unique scalars such that unique scalars, and this uniqueness comes exactly from the fact that V1, V2, Vn is a basis. Clear? So we have unique scalars which have this. This pair, this. So, this is a member of Rn, right? And we call this the coordinates. This is called the coordinates of with respect to the basis. Okay? And we shall write this as we will write this like this. Okay? So, you see, the notation is also very friendly. It says coordinates of x with respect to the basis b. Yeah? It is this. It has to be this member from Rn. Okay? Alright? Let's take an example. Let's look into R2, say. Yeah? This is the basis. So also is this a basis? Or why do before I do this, let me do this. Okay? Now suppose if I take xy from R2, this is x times 1, 0 plus y times 0, 1. If I have to write this as in terms of this, so if alpha times 1, 2 plus beta times 2, 1 has to be the same thing, then I have to solve this, right? Alpha plus 2 beta is x, and 2 alpha plus beta is y. So if I multiply this by 2, so x minus 2y, right? X minus 2y is 1 minus x minus 3 alpha. So alpha becomes x minus 2y by minus 3, and your 2 beta is x plus, so that is so this becomes actually where is the this becomes, this is 1 to right, alpha is plus 2x minus y by 3 of 2, 1, right? So you can check the calculations, I think they are right. So coordinates with respect to B of the point xy is actually this pair xy. Okay? Right? Whereas coordinates with respect to A of xy, this is actually 2y minus x by 3 and 2x minus y by 3. Okay? So you see, this is nothing else. Yeah.
We lost it down. How did you get the minus 1 back?
Which one? This one? Yeah. Yeah, I did the calculations. Just check, I did the calculations. If it is alpha and beta, then alpha plus 2 beta must be x, and 2 alpha plus beta must be y, and from there I checked it. Okay? So, this is nothing new. You see, when we started our coordinate geometry, so this is what your usual axis look like, right? Yeah? So in this place, when you try to construct, find a point, xy, so this actually means what? This perpendicular distance is x, and this height is y. Okay? But suppose, who asked you to tell you to take this coordinate frame? You could take, in fact, a coordinate frame like this. 1, 2, and 2, 1. Sorry. 1, 2 is somewhere here, okay? You could take this one, the blue ones, that is your A. And how do you get hold of the coordinates in that case? Well, that was where we did our old geometry. So you see, you take this and you take this. So this part is your 2i minus x by 3, and this part is your 2x minus y by 3. Okay?
Sir, could you please change the color? I can't see the yellow.
Okay. Okay.